Okay, welcome back, Physics 20s. Today we're going to start Chapter 7, which is looking at simple harmonic motion. This is an old clock. We don't really use many clocks like this anymore, but this ran off of a pendulum. You can kind of see that mechanism swinging back and forth, and it does so at a consistent time, which is allowing the clock to keep fairly accurate time. As you can see, it keeps following the same path back and forth, which could be used for timing devices or things keeping tempo in music. What do you mean? And a lot of different things follow this same repetitive path, which is called simple harmonic motion. And that's what Chapter 7 is going to be about. And today for 7.1, we're going to be looking at SHM, which is the same as simple harmonic motion. Whew, thank you. Finally, a physics concept that's simple. Well, yeah, pretty much. If we look at the definition, it's just a motion that is going to repeat itself. Something that swings back and forth, goes up and down, just going to repeat the same path over and over. So yeah, fairly simple. And we see a lot of different things in simple harmonic motion. We're going to look at these main three. If we have a pendulum, you can have that swinging back and forth and repeating that same motion. We'll also look at springs. If you hang one from the roof and you pull it down a certain way, so say this is in the stretched position here, it's going to go up and then it's going to come back down, keep following that same path over and over. And you could also have the spring laying down. You can compress it in this direction, it will release and go back to here, and it will keep going back following that path. So we're going to look at those three types of simple harmonic motion. But even though it's simple, it's still pretty interesting because this actually relates to circular motion, which we looked at in the last chapter. So let's see how that works. So let's say we have this circle, let's say it's like a bicycle wheel or some big loop, and I've put this red marker here, something that's kind of like sticking out of the wheel. And then I have a flashlight on the left side. And now I'm going to turn the flashlight on, and because of that marker, let's say that marker makes a shadow, this dark mark on the wall behind it, all right? So it's just hitting that one marker. Next, I'm going to spin the wheel, and watch what happens to the shadow is it's going to follow the circle there, but if we look just at the shadow, it's moving up and down really the exact same as simple harmonic motion if we were to take like a spring, pull it down and release it. It didn't quite work perfectly in the animation, but you can see it kind of follows the shadow. And if we were to look at this in real life and do this experiment, right here is where the shadow is going to be going its fastest because all of this velocity here is being shown by that circle. Their speeds are going to match. Now let's imagine that the circle was up here. I'm going to show how the speed of the shadow is going to be a little bit slower. The ball is still spinning around in the circle, or that red marker is still spinning in a circle at the same speed. All right, so it's staying at the same speed. But as it changes position from here to here, the shadow in this part isn't going to move very much. It's just going to have a small movement up and small movement down. So the shadow goes really slow here, fast here, and slow here. And this is what we see with simple harmonic motion as well. Whether it's a pendulum swinging back and forth or a spring up and down, it models that exact same change in speed. So we can just kind of put this shadow onto those other examples. We'll first start in the middle with the shadow right here. It would follow the same motion for a spring going up and down like that. We could then put it also on the pendulum and say if you were to view the pendulum from the bottom, so say you were looking here and you were just looking at this dimension, it would go back and forth in that direction, just the same as the shadow did. Again, being slowest at the endpoints and fastest in the middle. And we can have the same if we looked at a spring. It's supposed to be your eyeball looking this way down on the spring, and it's going to move in this direction like that if you compress the spring and release it. So just trying to show that same back and forth motion, fastest in the middle, slowest at the endpoints, can be modeled by circular motion and matches all three of these scenarios. Next, we'll just look at some terms. So here just kind of showing, again, that marker and the spring going up and down. Let's say the spring goes down to here and then up to there. We're just gonna look at some terms that describe this motion. So first of all, a cycle is one complete back and forth motion. So the easiest way to show this is if it starts up here, it goes all the way down, comes all the way up, and that's one complete cycle. It went from the top, bottom, back to the top, went through the whole motion. If you were to start at the center, you pull it down, or it's going down, and it releases and comes back up. I think some people interpret that to think that that would be one cycle because it's back to where it started, but it hasn't gone to the top of the motion. So I just go all the way up to the top and then come back down to where it started. Then it's completed the full path. So both of those would be considered one cycle. This one over here or this one over here. Now next we look at period, and this can be measured with T. You can kind of think of T for time. This is the time it takes to complete one cycle. So how many seconds does it take to complete one? And this cycle here from the top to the bottom of the top will be the same as over here from the middle all the way through the bottom, top, and back to the middle again. And that's gonna be measured in seconds per cycle. How long does it take to make one cycle? And the last one here, amplitude with an A, is displacement from equilibrium. I didn't mention equilibrium before, but it's if we take, I'll take another color here, show green, where you're kind of starting off with, where there's no forces acting on the spring or the pendulum, or kind of like the middle of the circle, where the object would stay there because there's no net forces acting on it. So just sitting at rest on the spring there, it's not being pulled down or pushed up, kind of like a pendulum just hanging down in the middle. Where there's no net forces is called equilibrium, which I'm showing with this green line. And the amplitude is the measurement from here. Now it's gonna go up a certain amount to its max height, which is gonna be the amplitude. And the amount that it goes below equilibrium is also the amplitude, and those are the same value. It's gonna keep going up and down from that equilibrium spot. So those are some terms we have to know. Looking at how the velocity, acceleration, and forces are gonna change, we're gonna look at next lesson. But today we're gonna look mostly just at springs in simple harmonic motion, not worry about pendulums quite yet. And we're gonna look at Hooke's law, like this guy. But not really, he doesn't really have any scientific laws. But the Hooke we are talking about kind of looks like this in the Cosmos documentary, kind of an odd looking guy as well. Whether that's accurate or not, I'm not sure. But regardless, he did make some significant contributions to science. You might remember him from Science 10 when we looked at his drawings of cork, when he looked at a cell and found, actually named the cell a cell in these early diagrams shown here. But anyway, what we're gonna be focusing on is his law with springs, which is called Hooke's law. And it's this, F is equal to negative kx. Now you're probably thinking, this is super familiar. We looked at F is equal to kx before in springs. It's just the exact same thing. It is, except for there is this negative sign. Why is that negative sign there? Well, we're gonna try to kind of explain the difference from last formula to this one. So previously when we looked at F is equal to kx, all right? So we had a spring and it begins here and we compress it to here. We said that x was the distance that that's going to be compressed, right? And to compress it that distance, you had to apply a force in this direction. So I'm gonna put F here and x there. And that meant that the displacement here that we have as x was in the same direction as the force. If you push something to the right, x is going to be in the right. So let's just say this is the positive direction and this is the negative. If you have a positive force going to the left there, you will have a displacement that is positive. So that's why we use this formula. It's looking about the force you apply to a spring. So I'm gonna put apply there. But now next, let's take another spring. And if we say F is equal to negative kx, this is no longer talking about the force you applied to the spring. It's talking about the force in the spring. When you push on a spring, it resists that. It pushes back against your hand or whatever you're using to push on it. So this is the restoring force. Restoring force. And that's what Hooke's law is looking at. So all this does is it flips the sign. So it's gonna start here and compress to there. We still have that x as our displacement. And now let's say that x is positive. It was moved in that direction. The force you applied was positive, but the restoring force inside the spring, which is what this formula is looking at, is in the opposite direction. We compressed it positive. The spring is pushing back this way. So the force that the spring is pushing is going to be in the negative direction. That's really the only change. Looking at the force you apply was our last one. This one is looking at the restoring force. That's just why we throw a negative in there. Okay, so we'll look at calculations with simple harmonic motion and the velocity and speed and forces in it a little bit next lesson. Today we're just gonna look at a spring because that's gonna be essential to looking at how the force on a spring changes, because that's gonna cause the acceleration and things like that. So we'll just do one example here. It says a spring with a spring constant of 100 newtons per meter is compressed 10 centimeters. Then a 750 gram mass is placed at the end of the spring and launched when the spring is released. You release the spring and shoots the mass Okay, first question is, what is the restoring force in the spring when it is compressed? And the next one is, what is the initial acceleration of the mass when it is launched? Okay, so we have our spring here, and it's going to be compressed a certain distance. So let's start with our formula of F is equal to negative kx. And remember, that's for the restoring force, and that's what it's asking for in the question. What is the restoring force? So we just plug in F is equal to, keep the negative there. K was in the question as 100 newtons per meter. 100 newtons per meter times X, which it said was 10 centimeters. We have to remember this should be in meters. So 0.10 meters. And so we just multiply those together and we get 10, negative 10 newtons. So that's the important part for that negative, because it was a positive 10 centimeters compressed. So the force is going to be in the negative direction. There are some multiple choice questions that one option could be plus 10 newtons, the other one could be minus. We have to know that's opposite to the displacement. Okay, so that's pretty easy for the first one. Finish that. And the next one was the initial acceleration of the mass when it's launched. We haven't really covered this yet. We think this is the amount of force that the spring is going to be applying, 10 newtons. So how much is that going to accelerate the mass? Well, we have another formula, F is equal to ma, and so we're just going to be able to use that. So I know the force is negative 10 newtons, equals mass times acceleration. Now I just divide by the mass, which was 750 grams, that has to be in kilograms, 0.75 kilograms, and then I'm getting a number of 13.3 repeating, negative 13.3 repeating, because again, it's going in the opposite direction that it was compressed for acceleration. So I'm just going to put negative 13 meters per second squared as our answer. Now, it doesn't seem too hard to calculate, but I do want to note one important thing about this is it said the initial acceleration, and that is what we calculated. When it's compressed at 10 centimeters, that's going to be the most force in that spring when X is the highest. If it's already extended out to, say, only 5 centimeters, there's not going to be as much force in that spring. So it's not going to be accelerating at the same rate. So the acceleration will decrease as the spring kind of runs out of force as it keeps extending. But its initial acceleration will be 13 meters per second. Then it'll go down to maybe like 10 and 5 and 3 until when it's fully extended, there's going to be no more acceleration. All right, so hopefully that lesson made some sense for you. You can try those practice questions. Let me know if you have any questions with those, and I will see you in the next lesson.